Motor Oil 101. This is going to cover the basics that a lot of people don't have, all these pieces. A lot of this will be familiar to most people, but there's going to be some things in here that you may not have known. And those little, we'll call it missing nuggets, can be an issue, right? If you're trying to choose an oil, you're trying to choose what your maintenance strategy is going to be. If you don't know all of these little details, you can sometimes get it wrong inadvertently. And we don't want people to get things wrong, right? The whole reason I do this is because I want people to be able to benefit from the knowledge that I was given, very fortunately, from my time working at Joe Gibbs Racing and working with the guys at Lubrizol and Afton and stuff like that. I had a tremendous amount of experience that I've been blessed with. And I want to share that blessing with everyone else watching so that they can make good, educated decisions so they can get it right to whatever level they want to be, right? Some people just want to be C's, get degrees, and that's okay. Some people want to be valedictorian, and that's awesome. And hopefully this will give you some framework to be able to do that. So with that said, let's hop in here to the presentation. Again, I'm not super used to doing all these live streams, but like I said, Motor Oil 101, these are the basics. These are the things that everyone needs to know about motor oil. In the future, we might do a Motor Oil 201 live stream and cover some more things like European specs and other little more detailed information. But for now, Motor Oil 101, these are the things that you need to know about motor oil. And for anyone that has any questions about, who I am, I am Lake Speed Jr. I'm a certified lubrication specialist and certified oil analyst. I do that through the Society of Tribologists and Lubrication Engineers. I've had those for quite a long time, actually. And like I said, my background is working with the guys at Joe Gibbs Racing. I formulated all the oils for Joe Gibbs Racing over a long period of time, that won many races, many championships. And then those same products not only were for race car stuff, we also did a lot of stuff for street cars that are used all around the world. It's called Driven now. So I formulated those products and helped develop that and did all the testing. And that's really the thing that I love the most is engine testing. We're going to talk a lot about engine testing in this because to understand motor oil, it's more than just chemistry. Spec sheets are helpful, but they don't tell you everything you need to know. If you're not testing, you're trusting. And I don't like that. I like to measure and know. So we're going to talk a lot about engine testing in this, but that's my background. Of course, I love testing so much that I actually ended up starting an oil analysis company to be able to do that. So we can do testing and give people real information that they can trust and be able to utilize to go forward. Because again, if you want to be a C student, that's fine. If you want to be valedictorian, it's going to take a little more effort. We can help you along that way if you're interested in doing that. Okay, next. Okay, I got to learn how to use StreamYard here. So this is what we're going to cover today. We're going to cover engine oil composition. What is in that quart of motor oil? We're going to talk about motor oil viscosity. There's a lot of misunderstanding around viscosity. I read the comments on most of the videos and I get, from customers sending in oil samples to be analyzed. I can tell there's a lot of misunderstanding about engine oil composition and viscosity. And of course, we just mentioned testing is so critically important. We're going to cover how motor oils are actually tested and how that testing then translates into motor oil classifications. So that being said, let's go ahead and jump right in to the functions of motor oil, because oil has very specific jobs and lubrication is only one of those jobs. Oil needs to not just lubricate, it's got to protect in terms of protection from corrosion and things like that. It's got to clean, it's got to cool, and it has to seal. Anyone that knows my experience, working with Total Seal and working with piston rings and engine development, the piston rings and motor will go hand in hand. Oil is the gasket between the piston ring and the cylinder wall. That's where that final piece of seal comes from. So the relationship, and that's one of the key areas of oil that people miss, and especially when it comes to engine performance and durability, is how that oil interacts with the piston rings and the cylinder wall. And of course, the fuel is the enemy of all that. The fuel is trying to wash all that away. So it's a really complex tribological environment happening there in the pistons and the cylinders and the rings and the liners and surface finish and metallurgy. All those things matter. Of course, that's like a motor oil 301 class. We won't get to that today, but understand that motor oil has these really important jobs. It needs to lubricate, it's got to protect, it's got to clean, it's got to cool, and it has to seal. Right. And it's got to transfer some power too in there. Right. It's also a high, motor oil, especially in today's engine, is functioning as a hydraulic fluid. And that is a really important characteristic. So if the oil becomes aerated, the hydraulic portion of it isn't going to function as well. So there's a lot of things that motor oil has to do. And because of all of those important jobs and that wide variety of jobs, it's going to need more than just base oil. It's going to need additives. And that's the key. Motor oil is really two things. It's base oil and additives. Now, when it comes to a synthetic oil, we'll call it a PAO, synthetic oil, we're only talking about 3 companies that really make synthetic base oil, the PAO synthetic base oils. And we're going to talk about some of those differentiations as we move forward, because the term synthetic is used really generically. And that's the truth. It's a generic term, right? If you're talking about a Group 4 based product, you're talking about a base oil that came from either Chevron, Phillips, Ineos, or ExxonMobil. Those are the guys who make it. Now, the additive package that goes in there is going to come from one of these 4 companies: Chevron Oronite, Infinium, Afton, or Lubrizol. Those are the big 4 additive companies that create the additive packages that go into the oil so that it can do the jobs that are required. Clean, cool, protect, transfer, power, seal. It's got to do all those things. How does it do all of that? Well, the base oil alone usually can't do all of those things. It's the combination of the base oil and the additives that help make all that possible. And again, depending upon the needs of the application, you might bring in different base oils or different additive packages in order to meet the needs of the application. Now, one of the little fun things is that, base oil is that primary part. We just said there's a lot of things that come up with that additive package. So when you look at what's in a bottle of oil, a large percentage, anywhere from say 75% to 95%, is that base oil. So base oil is really important. But that DI package, that we call it the detergent inhibitor package, the zinc, the moly, the boron, all the other stuff, that's that DI package. That's what, Lubrizol, Afton, Oronite, Infinium, those guys make those DI packages. And we'll cover that in a little bit. But then you also have your viscosity modifiers and your pour point depressants, things that help change how the viscosity of the oil works in service. So all those kind of come together. And if you think about it, say your traditional passenger car motor oil, you're going to be somewhere in that 10 to 13% treat rate range in terms of how much of the DI package is in the oil. And then the viscosity index improver and all that stuff could be another, 8 to 12% or something like that, depending upon what viscosity grade it is going to factor in there as well. But then your heavy duty, your diesel stuff, and we're going to talk on some diesel stuff toward the end. It could be, as low as 12%, all the way up to 20%. So typically the diesel packages have a higher treat rate. And the main reason for that is diesel oils have more dispersant additives. Now hear me out. The number one source of wear in a diesel engine is from soot. Soot is the enemy of your diesel oil and your diesel engine. That's why there's an actual test that we'll actually cover later, and bore polishing. That soot-related wear is a big issue in diesels. So diesel engine oils contain a greater level of dispersant chemistry in order to keep that soot suspended finely so it doesn't agglomerate and turn into larger, hard carbon particles that can cause abrasive damage, cause bore polishing and other forms of wear in the engine. So again, diesel engine oils are different. That big change in treat rate is usually due to the extra dispersant chemistry added to it more than anything else. That's the main differentiator. There are other little differences in there too. That I'm saying they're all important differences, but that main differentiator is the type and the amount of dispersant in a diesel oil versus a passenger car oil. So here we go. Next slide. But here's a really important thing to keep in mind is that all of these products, and I happen to formulate all three of them, they all contain one common base oil. So when we go back and we look at, Chevron, Phillips, or Ineos, or ExxonMobil, or any of the other maybe Group 3 base oil suppliers, like Petro-Canada and Calumet and others, that same base oil that can go into an engine oil can also be used to make an ATF or a gear oil. What makes those products different is not just only viscosity. For example, that 520 that we're showing there in the slide is about the exact same viscosity at 100 degrees Celsius, 212 Fahrenheit, as the ATF is. So they're the same viscosity grade. They actually use the exact same base oil. Like the primary base oil is the same. It's the additive package and the other parts of the formulation, the ancillary parts, that make it different. So the VM would be different. The co-base stocks could be different in that regard. But the primary base stock is the same in all three of those products, including the gear oil. So it's important to understand that there isn't a best oil. There's not a best brand. It's about taking those chemical needs and matching that up, or taking the chemical properties and matching it to the needs of the application. That's the real key in terms of making an oil function well for its intended application. So I hope you can see that these are different applications. They all have different needs. It's the additive package that's going to make the biggest difference here, as opposed to the base oil. All right, so let's move on to the next slide here. So speaking of base oil, all right, everybody get ready. I'm gonna get comfy here, because we're gonna stay here for a little bit, and this one's going to be really good. Okay, so when it comes to base oils, we will cover the API viscosity grades. You pretty much have two types of base oils. We're gonna say you got your conventional mineral base oils that are refined products. Then you've got your synthetics and other stuff, right? So you basically have something that either is refined crude or it's not. It's something else. So that's kind of define it that way. So when we look at conventional base oils, that's refined crude, what you're talking about is taking that crude oil and you're putting it into the refinery, and we're heating it up and we're boiling the crude, because crude oil is a combination of millions of different molecule types and structures. And there's different boiling points for those different structures. And different crude oil, as we mentioned in the video on the history of motor oil, has different characteristics, different properties, because there's different molecule structures in there. So the refining process, that distillation, is separation by boiling point. And what turns into lube stock is down here at the very bottom. We're like, butane, lighter fluid, gasoline, diesels, other things, kerosene goes off the top. What comes out the bottom is the heavy stuff, and that's the lube stock. And not every refinery actually makes base oil. And some crudes, have some stuff that can yield lube oil. Others don't. And there's different processes you can go through. But the traditional process is basically straight vacuum distillation and solvent refining, solvent extraction to kind of get some of the nasty stuff out. That's your old school Group 1, which we'll cover that in a little bit. But remember this slide, because this is really important to understand how base oil is made that comes from crude. Now, when you think about that, only a half a gallon of crude oil, or of lube oil, comes from a barrel of crude. Now, a barrel of crude is only 42 US gallons. And of that barrel of crude, if it does make lube stock, only about a half a gallon is going to come out. So lubes are very low production in terms of what comes from all the refineries. So just because you drive by a refinery doesn't mean they're making lube oil, and they're probably not making a whole lot of lube oil, even if they are. So keep that in mind. So when we look at the API categories, let me caution you right off the front, because I see this all the time. There is a thought process that says, well, the higher the number, the better that it is. Stop. Break that thought. Put that aside. Look at these as differences. There's 5 different categories that have chemical differences. Those differences can be used for good, however you need to match them up. Maybe you get a great example. So groups 1, 2, and 3 all begin life as crude oil. I mentioned earlier that just that number group 1 we talked about going through with the solvent extraction. That's your old school conventional base oil and how it was made prior to the early 90s. But then in the early 90s, around that time period, hydrocracking came in, and that technology allowed for some crudes to now be able to make lube oil that couldn't make lube oil before, and to create some different kind of products that had a little more thermal stability, that had lower sulfur, that could create a higher viscosity index. So where old school group 1 was really, determined on the source of the crude would be the only thing that determined the outcome. With the group 2 hydrocracking process, you could begin to have some flexibility on what that crude input was and not have as much input on what the output was in terms of the chemical properties. They could begin to refine it and narrow it down. And so today, almost all conventional base oils are group 2. That has a higher level of viscosity index, has a lower level of sulfur. Those are typically good things, less saturates, higher saturate rate. But what happens is, as the saturation goes up in terms of chemical, that's basically there's less double bonds, it's less reactive, less places for things to go wrong, if you will. The downside to that, because I said it's easy to look at this and just say, well, the higher the numbers, obviously they're all better. There's an inverse though. The higher the number of saturates, the greater the saturation is, the less solvent it is. So what happens a lot of times is that there are applications where a group 1 base stock actually works better because of the very high level of solvency. It can create less deposits in application due to the fact that the higher solvency allows for less varnish formation. Now, the thing is application dependent. I'm not saying that's the case for in all applications. It's certainly not. The higher the temperature of the application, that's where that flips over. That at really, really high temperatures, that group 1 is going to break down easier and begin to form deposits. So it's all about, somebody says, I think, application always dictates chemistry. And this is a great example of that in some cases, group 1 is superior to even a group 2 or even a group 3 or even a group 4. If the solvency is the main need of the application, because a group 1 has greater solvency than a group 2 or a group 3 or a group 4. So it's all about balancing these needs and creating a balanced package, because each of them had their own things. So that group 3, that severely hydrocracked process, that is known as a synthetic, at least in regards to engine oils, pretty much around the world now, right? I mean, it's the U.S. started here. This is the Castrol Mobil lawsuit that we mentioned in our most previous video on the 50 years of Mobil 1 and the history of synthetic oil. We talk about that in detail there, so I won't rehash that right now. If you want to go look at that, I'll leave a link for that in the description box at some point in time. But that last video about the history of Mobil 1 and synthetic oil, we cover that in great detail. The group 4 is your PAO. That's your polyalpha olefin synthetics. We're actually going to be doing a video on that really soon. We made a trip down to Houston, Texas, and visited my buddies at Chevron Phillips. and they gave us the full tour and we got into all the details. So we'll cover that in a future video. And then group 5 is everything that's not in the first 4. So yes, esters are in group 5, but there are other things in group 5. Alkylated naphthalenes are in group 5. Vegetable oils would be in group 5. Naphthenics are in group 5. So just because it's group 5 doesn't mean that it's better than the others, because a vegetable oil is certainly not better at lubricating an engine than a group 1 base oil is, or especially a group 2 or even a group 3. Same thing goes with a naphthenic. Naphthenics have very low viscosity indexes. They're not going to be good. They're great for cleaning, but they're really not good at other things in terms of like having a high viscosity index. So that's why I cautioned earlier about there are 5 different classifications. They all have their own pros and cons. And it's the job of the formulator to balance all those things in order to create a product that meets the needs of the application. Now, speaking of the needs of the application, this is where synthetic oil can really do a great job, because synthetic oil has 4 key advantages over conventional mineral-based oils. When I say synthetics here, I'm talking about your PAOs and your esters, and usually they're used in combination. Now, some applications use straight esters, like jet turbines and things like that. Typically motor oils, we're about motor oil here, motor oil 101. When you're talking about a synthetic, you're talking about a PAO, there's going to be a ester used as a co-base stock. Is typically what you see. There are some full ester oils out there. Redline would be the one that's been the most popular, been out around the longest. It's a full ester formulation. The advantages of those is that you have better temperature stability, right? Synthetics, as you can see, can operate at a higher temperature before beginning the thermal breakdown. Oxidation doubles every 18 degrees, roughly Fahrenheit, you increase the temperature of the oil. So every 10 degrees Celsius, the oil temperature increases, oxidation rate doubles. Synthetic oils can operate at a higher temperature without that oxidation rate killing you because of it's more thermally stable. And you can see that from a mineral oil to the PAO to the ester, they can just keep bumping up in terms of oxidation stability in service. They also typically have a higher viscosity index. So a PAO and an ester typically have a higher viscosity index than conventional base oils. They also have a greater specific heat value. So PAOs, really, this is their big standout, is they can absorb more heat from the part. And that's a big advantage. Then they can usually reduce friction, right? So PAOs actually have very low internal friction. And so they can usually drive the friction way down. And then you can add some of that polarity and some of those ester chains can be really good at providing enhanced lubricity. And there's usually a trade-off between lubricity and thermal stability, though, because there's a wide range of esters. So we're again talking in here in massively broad terms, but the key is when you have extreme temperatures, this is a question I get all the time. When you have extreme temperatures, either extremely cold or extremely hot, that's where the synthetics are going to provide more of an advantage compared to a mineral oil. As you see, at moderate temperatures right down the middle, there's not going to be a giant difference in how they all perform. But at the extremes, that's where they can really perform. So think about today's modern direct injection turbocharged engines. This is where synthetics have a big advantage over conventional mineral oils because they can handle that higher temperature that's the oil is being exposed to from the turbocharger. All right, let's move on to the next one. Okay, so that was kind of the wrap up of, hey, that's the base oils. All right, we know we need to have a good lubricant. We got to have a wide operating temperature range. We got to have thermal stability. Those are the key things. Now let's talk about that DI package, that next level. What makes it a motor oil, not a gear oil or transmission fluid? And how do we address the needs of that engine in order to get better life and better performance from that engine? And the way we do that is by adding in things like dispersants we talked about before. Because even direct injection engines. This is one of the changes here in the last probably 10 years, is that direct injection engines also create soot, but it's not the same soot as what's in a diesel engine oil or what a diesel creates. So we're not using the exact same dispersant chemistries that you use in a diesel, but you're using some stuff in a passenger car oil now that would have been maybe in a diesel oil before. Different treat rates, maybe different co-base stocks and chemistries, but we now have to address soot in a gasoline engine oil where you didn't have to do that before direct injection became became commonplace. So now that we have DI engines, we need to have, good dispersants to handle the soot. We also need to have the right level of detergents. We're going to cover that in a lot here. You're going to spend a lot of time on that. But you also need to have things like antioxidants. We can have a good base oil that's got great antioxidant performance, but we can add in antioxidants, just like eating blueberries or pomegranate seeds or whatever you want to do to help boost your own immune system and antioxidants in your own bodies. We can do the same thing here. We can add in antioxidant chemistries that make the oil able to withstand that temperature without breaking down, that extends the life of the oil, that helps prevent deposit formation and things like that by opening up that operating window. Really important. Of course, we've got anti-wear additives like ZDP, stuff like that. We also have friction modifiers. Primarily molybdenum is the main one these days. We're going to talk about that in another video coming up in great detail. So I don't want to give away everything today. But then you also have things like foam inhibitors, right? That's a big issue when you get to higher speed engines, especially we mentioned earlier about, oil. One of its jobs is being a hydraulic fluid. So you need to have good anti-foam, good air release as well to enhance and aid the hydraulic fluid performance of the oil. So we need to make sure we have all these things covered. So that's what the Lubrizols, the Aftons, the Ornites, the Infiniums of the world, that's what they're doing, is they're creating these packages that have all of these additives in them to meet the needs that are set by API or ILSAC or ASEA or individual OEMs. They're taking that and saying, okay, these are the base oils being used in the market. How do we create a package that can meet these specs to deliver engine protection that can fit into any of these base oils in the market and be able to provide, a high level of performance that meets customer demands, and it can make things happen. So that's what their job is, which is a super cool job because it requires lots of testing, so much testing. We're going to get to that in a little bit, but just to kind of get a little bit deeper understanding of what this stuff is and how it works. The first thing is about ZDP. So we could talk for an hour just on ZDP. Easy. So we'll save ourselves from that. If you really want to know more about ZDP and how that, too much ZDP is actually a bad thing for your engine, you go check this video out that's on our channel. It explains that in great detail. Again, we won't rehash everything because I could literally be here for 4 or 5 hours covering everything if we really try to get to it. But the key thing to understand is this. ZDP is not alone in the engine oil. There are detergents. There are dispersants. And these things are all interacting. All of these different molecules, from a detergent, dispersant, a ZDP additive, a molybdenum additive, they're all polar. So they're all trying to work on that surface. And like, for example, in this quote, read the quote right here. I'll just read it real quick. All right. Engine oils contain the anti-wear additive zinc dialkyl-thiophosphate, and it is well known that this additive reacts rapidly with rubbed ferrous surfaces to form a thick iron and zinc phosphate base coating. To be effective, a friction modifier additive has to form a friction-reducing surface film, not on the ferrous surface, but on the zinc phosphate one. So all of these things are layering and taking place. So if you got a friction modifier that someone's testing in some kind of device, and they're just testing it by itself, it's not telling you the truth, because that's not what it's going to be working on. It's not going to be working on that metal surface in the testing device. It's going to be working on a metal surface that's covered with a ZDP film. It has to work with the ZDP, and not all friction modifiers work effectively with ZDP. So we're going to cover again. There's a lot of things I'm going to say, hey, we'll cover that in a future video, because there's so much here that we could dig deep into. And I promise you that in the coming, this year, in 2025 and in the future, all these things, there will be a more deep technical dive into that to explain it better. But today is just Motor Oil 101. We're high level surface. So understand that all this stuff's going on. And here's a really key quote too, before we move on, is that it is true that constant switching of brands is discouraged. A key reason is the risk of negative synergies occurring when two different additives are trying to interact with the same metal surface. Think about that. These additives, additives are on that surface. You drain that oil out, additives are still on the surface. You put in the new one. We talked about the very beginning of the video. That's the case, right? That these additives can interact with each other. So it takes a little bit of time for them to be established. So if you're constantly switching back and forth, putting in different additive packages because you're using different brands, it can actually cause more wear than if you just had the same additive package and you're just replenishing it. It's not having to be changed out. There's no additive competition there. We will actually show this in a future video because we did some tests, and this actually jumps right out. Pretty amazing during that test. This is also why when it comes to, say, like break-in, like one of the keys to a real break-in oil is low detergent, because the detergents are competing. They're also polar. They're competing against that zinc. So that's what made the Gibbs break-in oil something unique in the marketplace that works so good to address the flat tap camshaft issue. Wasn't that it had more zinc in it. It was that it was low detergent. There were lots of higher zinc options around then. Cams are still going flat. The issue is the zinc detergent balance is what really makes a difference in terms of how things work in terms of wear protection. And you can see that right here, that using a higher zinc diesel oil with all that dispersant in there to break in the cam, and then just running a regular API oil, look at the level of iron, the crossover point between the additives and that red line. So anything to the left of that red line is the additive film on the surface of the part. So that's with it. We'll call it traditional chemistry, where you're not using that, we'll call it break-in chemistry, where you're really changing the balance to an extreme just temporarily to try to build that additive film up initially. Now let's look at what happens. That red line moves way to the right. How much more additive film there is when you have that change in zinc detergent balance. They all had zinc, they all had detergent, but you changed the balance, and that changed the film formation massively. And this is one of the key things that's happened in the last 10, 15 years, is if you go back to API SM, you typically had, calcium levels, upwards of 3,000 parts per million. You had really, really high levels of detergent with only 800 parts per million maximum on the ZDP. This is when all the camshafts went flat. It's because of that giant mismatch, that imbalance zinc detergent. Well, API SN came along and it started to move that backwards a little bit, right? That detergent level started to come down a little bit, and it wasn't as aggressive because people were starting to understand, wait, hey, this calcium stuff is having an impact, maybe in the direction we didn't want it to go. Then you get to API SP. With API SP, now we have the full understanding that those high levels of calcium actually cause low speed pre-ignition, the type of detonation in turbocharged direct injection engines that can destroy the engine quite quickly. So what happened is those ZDP levels stayed the same, but the detergent levels went down, the calcium levels went down, and the wear protection went up. We saw better wear protection from the same brand, same viscosity oil as an API SP package compared to an API SM or SN package. Motor oil has gotten better in terms of wear protection, and I am speaking directly about a flat tappet engine. All that wear testing was done in a flat tappet engine. Now, don't go using API SP oil to break in a flat tappet engine. Zinc detergent level still isn't ideal for that. But once it's broken in, they will do a good job because of that change in chemistry balance in the additive package. That's what's so important. Okay, so talked about base oil, talked about the additive chemicals, right? The next part is viscosity modifiers. This is a big part of what's changing. So we really got to talk about viscosity 101 before we dig into the polymers. So the key thing to understand about viscosity 101 is all oils get thinner as they get hotter. Inversely, they all get thicker as they get colder. That is, don't ever forget that. Even adding a viscosity index improver does not make the oil get thicker as it got hotter, right? A 20W50 does not mean it's a 20 when it's a cold and it's a 50 when it's hot. That is not the case. I'll say it again. A 20W50 does not mean it's a 20 when it's cold and a 50 when it's hot. Because if it did, that means the oil would have gotten thicker as it got hotter, and that does not happen. All oils get thinner as they get hotter. So we need to dig a little bit deeper to understand what is that 20 and how that it's not the same test as the 50 because they're different. Because it's actually a 20W and then the 50. And the W does not stand for weight. It stands for winter. So let's jump into this next slide. There we go. Again, just showing all oils get thinner as they get hotter. And in the racing world, you can really see this, that like a 0W, well, 5 used to be like a made up number back in the day. That would be probably like a 0W8 now, actually. Like a 0W8, if you will, could be a pro stock engine oil. But the operating temperature of that engine is 100 degrees Fahrenheit oil temperature. Whereas the NASCAR engines were around 220 degrees. And then, say a World of Outlaw sprint car engine, oil temperature is 300 degrees. So they're using a 15W50. And the crazy thing is, of those three oils, in terms of the operating viscosity, that 0W is the thickest operating viscosity of the three because the operating temperature was so low. At 100 degrees Fahrenheit, that 0W was right around 12 centistokes flow measurement, where that 520 at 220 degrees was around 8 centistokes flow measurement. The 1550 at 300 degrees was right around 7 centistokes. So the thinnest viscosity grade was actually the thickest and operating. So it's all about operating temperature. If you got to know your operating temperature to be able to really know what your operating viscosity is, and then that's a really, really important part of what's going on. So if you're up in, Edmonton, Alberta, Canada, that lower W grade is really helpful for you unless you got a block heater to make everything warm before you crank it all up, but even then it's important to have an oil that can flow well at low temperature in the extremes of that. Now, if you're down in South Florida or South Texas, then that doesn't really bother you too much, right? You're going to be more worried about that high temperature performance and stability, and can it hold its viscosity and not shear and not break down mechanically in on the other side. So different operating environments, different chemical needs, application always dictates chemistry. You can't beat that dead horse enough. All right, let's go check out the next slide here. So we're just kind of mentioning it that in the old days, you literally had seasonal oil changes. You had your winter grades, your 10Ws and your 20Ws for the winter, because that's when you ran that thinner oil in the winter. Then in the summer, you used your straight grades, your 30 and your 40 and your 50, depending upon what your application was. The idea of multi-grades is that it could have some characteristics of both, right? A 5W20 means that it has the winter performance of the 5W, that better low temperature properties, not flow properties. We're going to get to that, but still can maintain the summer high temperature viscosity. So it could kind of try to do both. And it does that by using viscosity index improvers or viscosity modifiers. Now, here's the thing. We got to understand how both of these tests, or both of these grades, the winter grade and the summer grade, they're tested different. So the summer grade is actually a flow temperature, or flow measurement. So we're using a viscometer here, and you're pulling the oil up the capillary. The oil is at 100 degrees Celsius. That's 212 degrees Fahrenheit. And you're flowing the oil from point A to point B, and you're measuring the time it takes the oil to travel that distance, right? That's called a centistoke. So high temperature viscosity measured at 100 degrees Celsius, recorded in centistokes. Your low temperature viscosity, your W grade, is measured using a rotary viscometer. It's the resistance to turning. Think about your crankshaft trying to turn over in the vehicle, and it's reported in centipoise. So 2 different viscosity grades, 2 different measurements. That's really important to keep in mind when you're looking at all of this. And the next little curveball is the pour point depressants. So depending upon the base stock, so say a PAO, because it was built in the lab, essentially, right? You're taking natural gas, you're taking decene gas or dodecene gas, and you're building up a larger molecule from that smaller molecule. In fact, the GTL, the gas or liquids that's used, that Shell has and many others are using now too, is taking natural gas and building up a larger molecule from that. When you're constructing a molecule, there's no wax. So those base oils don't really need pour point depressants. But your mineral base stocks, even though they're solvent refined, a group 3, if you can add in a little bit of pour point depressant, it can help lower that pour point, because there still could be some residual wax type structures in there, and it keeps them from agglomerating and basically changing the viscosity of the oil. So this can, by adding some pour point, it can actually lower that W grade, allow that rotational torque to be a little bit freer at low temperature, so you can get a little bit lower W grade out of that same base oil combination that you would otherwise. So speaking of winter grades, so you got the 0W, the 5W, the 10W, 15, 20, 25. And you can see here's are the temperatures at which the rotational torque is measured. And there's a max. There's a if you at say -35 to be a 0W, it cannot be above 6,200 centipoise. If it's that or lower, you can call it a 0W. It's like a 0W40, for example, is really hard to make, because that base oil viscosity has got to get there. And it's easy to push itself out of that 0W, because that 6,200 is really hard to hit at -35 degrees Celsius, which, by the way, I think it's negative 35 or -40. I forget which one it is now, off the top of my head, where Fahrenheit and Celsius are the exact same. It might be 35 or maybe 40. But yeah, you can see that it's basically 10-degree increments. So you start off at -35 and you start adding, warming up 5 degrees at a time, all the way to get to 25. And that as you get warmer, below freezing the Celsius scale, that limit goes up higher and higher and higher and higher. So it's being a little more generous, knowing that 0W, it has to be able to protect at extremely low temperatures. So back to what I said earlier, what's your environment? If you're in the North Slope of Alaska, you're all about 0W. If you're in South Texas, probably not worried about it too much, because you're not going to see these kind of temperatures. The 5W, the 10Ws are going to be more than you ever need, more than likely, depending upon where you are. Now, on the flip side, the summer viscosity grades, you can see that even those old winter grades, they still would do a minimum test, if you will, on that high temperature, because all those oils that eventually warm up in the engine, So you see that a 0W had a minimum of 3.8 centistokes viscosity once it was up to operating temperature, which is why you never really saw those before. But you could see, a 20W would have a 5.6, or a 25W had a 9.3, which those numbers are pretty common today, because a 5.6 today would put you in the 0W8 range, actually. Or it could even be a 0W12, depending upon what the high temperature, high shear value is, because that's the thing that adds in. When you look at the summer high temperature grades, we're measuring that viscosity, that flow measurement at 100 degrees C, and there's a min and there's a max. Like say, for example, look at the 30 grade range, 9.3 to 12.5 centistokes. That's the flow rate range. But you also have to have it, well, it has a minimum high temperature, high shear. So that's at 150 degrees C. And as again, now we're rotating it, we're shearing the oil mechanically a little bit to see how does it thin out. So you see that it goes from basically a minimum of 9.3 centistokes flow. We're dropping the 2.9 centistokes, that's not centistokes, 2.9 centipoise as it rotates down. So you think centipoise, again, back to that summer or the winter grade, you could have been at 6,200. Now we're down to 2.9. They're both centipoise. Just showing you that rotational difference is huge. All oils get thinner as they get hotter, and we're trying to make sure we're keeping enough viscosity to protect those parts for the speed and the load that engine's designed to handle. So that's why we have these viscosity grades, and which is why they're important. So that nomenclature, we kind of beat this dead horse a little bit. We'll move on real quick. W stands for winter, and we got our summer grades. So you're matching them all up, and that's what makes all these things kind of tick. Now, a little bit of viscosity 201 here. I mentioned all these viscosity index improvers. So what the difference between, say, a 0W30, a 5W30, and a 10W30 is the amount of polymer and the viscosity of the base oil. Say, for example, that 0W30, you could probably be using a 4 centistoke base oil. That means that base oil flows 4 centistokes at 100 degrees C, right? 212 Fahrenheit. That's what the viscosity of the base oil is. But to be a 30, I've got to be at least 9.3. So how do I get there? Well, I got to add a lot of viscosity index improver to get my viscosity up to that. So the wider the split in the multigrade, it usually means there's more polymer in the oil to get there, because that lower viscosity base oil, to get the W grade, to get it to be able to rotate still at low temperature, now I got to add more polymer to make up for that at high temperature. So you see, like a 5W30, that could have been maybe, say, 6 centistoke base oil. And now we're only having to add, 3.5 centistokes in order to get it to above 9.3 to make it into the 30 grade range. 10W30, it could be 8 centistokes. And now we're only having to add, a couple of centistokes worth of viscosity index improver. So that base oil viscosity of a 10W30 is really different than a 5W30 or a 0W30. You think about it, that even more difference as you change those viscosity grades. In a straight grade, no polymer. Doesn't need it, right? It's a straight grade. There's no polymer. That's what it is. So understand that when you see the shearing, because this is the other thing, the more polymer you put, oh, wow, it was whoever did that, that was amazing. You did not need to do that, but thank you very much. The more polymer you put in the oil, the more it can mechanically shear. You think about a rubber band. That's what these things kind of are, in a way. The more you stretch it, what happens? It thins out. Stretch it too hard, what happens? It breaks. Once it breaks, that's permanent viscosity loss. And we do cover this in great detail in our vanishing viscosity video, where we go and we show that. So again, each of these topics I could probably spend a whole hour on by themselves. So if you want to know more about viscosity breakdown and shearing, Go check out that video. It's really great. I'll leave a link for all this stuff in the description box below. And one of the other changes to viscosities is the addition of the 16, the 12, and the 8 grades. So I think it was going back to around 2014 or 15 or somewhere in there is when they, 15 is when they updated the SA viscosity grade range, and they added the 8 and the 12 and the 16. But API didn't even adopt the 0.8 and 0.12 for the US market until about this time last year, right? It was, it had been a while, right, before they did that. I think it was September of 23 is when that came in. So it was pretty new, is or November of 23 when they adopted that. So it hasn't been a totally long time, only about a year or so since they brought in those grades. But what they did was when they brought in the 0.16 is they went from using that starburst and the donut alone. Now they added the shield instead of the starburst, because the starburst are the ILSAT grades. So those are the fuel economy grades. So you'll only see that starburst on oils that are 10W30 or lower in viscosity. That only goes down to 0.20. So from 10W30 to 0.20 are the ILSAT grades that have that starburst symbol. The 0.16, 0.12, and 0.8, they all have that shield over there. That way it differentiates it, because those lower viscosity grades, the 16, the 12, and the 8 are not considered backwards compatible. Where all the ILSAT grades, they have backwards compatibility built in, where they run reference oils and things from previous generations to make sure that those oils meet all the same requirements or exceed the requirements from the previous specifications. Like I said, oils have been getting better over time. With the SN or SM stuff, there was a deviation there that really negatively affected high performance cars and racing cars and classic cars. That's been corrected now. The SP has addressed that. And someone mentioned in the chat about SQ. SQ is coming out. We're going to touch that in a little while. It's coming up in the spring. All those things are coming. Actually, right here on this slide. Boom. SQ and GF7 debut this spring. And it's just a tweak, where SP and GF6 was a makeover. It was like an extreme home makeover. They went in and there was all kinds of new tests put into place because of, modern direct ejection, turbocharging engines, the soot-related issues with chain wear. They had to come up with all new engine tests to address the hardware needs of modern hardware. That was a massive undertaking. It took it might have been like 10 years to get that specification out. It was hard, but it made a big difference. It improved motor oil. With SQ, there aren't any new tests. The one big variation is now that the low speed pre-ignition protection test is going to be run on both new oil and used oil. Because we've started to see that in the field, some engines, some manufacturers, some oils, their LSPI protection would change as the oil aged. So new, they all passed the test. Used, some of them not so much. So with SQ, all the oils now had to pass the test, even used. So that's the biggest change with SQ and GF7 compared to GF6 and SP. I mean, there's some other spec limits there. They keep trying to get the box tighter, right? Making the oils better. So everyone, OEMs want to have better oil. Consumers want better oil. So all that's coming together. Oil's getting better as these things go forward and move on. And to give you a little idea who we're talking about here, let me push that back up to big screen. Okay. Who makes these symbols? What's driving API? So API is working with a whole bunch of other people. So the API is the American Petroleum Institute. but it's also working with AAM, which is the Alliance of Automotive Manufacturers. That's the OEMs, right? Then you got the American Chemistry Council. So they're kind of like on the sideline judging how to make sure we're doing things right. You've got the Engine Manufacturers Association. You've got ILMA. You got SAE. So ILMA is the Independent Lubricant Manufacturers Association. They're not the ones who are the majors. So the majors who are doing the pulling oil out of the ground, running the big refineries and all that, those guys are in API. The independent blenders are in ILMA. So this whole consortium, of course, SAE is the Society of Automotive Engineers. They're definitely on the engineering side of everything, doing the testing. And then you also have ASTM is also in this mix. They're the ones that are running the test, developing the test and running the test independently to make sure that the oils are capable of doing what they're intended to do. So this whole group works together. And over time, they just keep finding what are the issues. Let's address them, come up with tests, let's define it, work on it. So it's really an interactive group where you've got SAE, ASTM. Like I said, they're working, trying to find what are the issues, how do we solve them, how do we create it. And then, of course, the OEMs are giving feedback. Hey, we see this issue in the field, this warranty concern. Let's address that. Sludging and valve covers or whatever it is. Let's address these pre-ignition. That's where it came from. It's feedback from the OEMs. And of course, then it goes back to the API. They come up with, here's the standards. We're going to administrate it and make sure that it goes to the field so that people can know that they don't need to know all of this stuff to be able to choose an oil. They just need to know that, my owner's manual says I need an API SQ 5W30. Then you should go buy any API SQ 5W30, and it should be sufficient. C's get degrees to do that job. If you want to be valedictorian, just had to take something different, but at least it can give everybody that minimum level of protection. And you don't have to be a motor oil geek to understand any of this kind of stuff, right? You're supposed to be simple, make it easy for the public to understand and be able to do a good job, right? And I think they've done a really good job of that, by the way. All right, I'm going to say that over all the years, motor oil has gotten better and things have gotten, less complex, easy to understand and just use. Because you think back to 1945 and that base oil was solvent refined. There was hardly any additives in the oil. I mean, ZDP wasn't even invented until 1941. And it was invented as a bearing passivator. It wasn't even invented as an anti-wear additive. There was a happy discovery later on that it happened to be really good at anti-wear protection. So there was hardly any additives in the oil back in 1945. Really, there wasn't much of a spec at all. Really, everything was based on where did the oil come from. That, if it was in Pennsylvania, then that was a better oil because it typically had a higher paraffin content, so it had a higher viscosity index compared to maybe a California crude, which would have been more naphthenic and maybe not as good in terms of that regard. So the well location, the crude source, all these things were factoring in, and you literally had 1,000-mile drain interval, right? The whole Kindle 2 fingers was because Kindle could go 2,000 miles because of it. Just they had a de-waxing technique and some things that allowed that oil to go a little bit further from the wells they were pulling it from, right, out of Pennsylvania. So it's a little bit different. Engines would maybe live 50,000 miles. And you had stuck rings, you had high oil consumption, all kinds of deposits, high wear on cams and lifters. I mean, everything was junk in 50,000 miles, right? That's how the engine rebuilder world took off, is because you had all these cars and these engines, they were wearing out at a rapid rate. So they had to be rebuilt. In-frame rebuilds, all that stuff came out of this era. By 1965, things had improved quite a bit. You were still using solvent refined base oils, but now you had a more robust additive package. So you're around 10%. You had detergents, dispersants, antifoam, anti-wear, even had some friction modifiers, maybe in some really high-end oils coming in. But primarily at that point in time, you had detergents, dispersants, anti-wear additives, antifoam, antioxidants. Those basics we talked about earlier, they had them all in there. Pretty standard block and tackling. You had industry coming up with dyno test to be able to prove this stuff out. You had that very early API specifications coming along to be able to really understand, hey, here's a good oil. Those are bad oils. Because before then, there were bad oils out there. 100%. Now we're coming up with standards, trying to make it better. By this point, you've got, 10W30s were, multi-grade oil, so you didn't have to change oil seasonally. You've got the motor severe category coming in, and you got a 3,000-mile oil change interval. This stuck around for a while, didn't it? Right? You got to this point, and things stuck around and began to persist. You still had, thickening oil and other issues going on. Compare that to today, though. Today's oils, you've now got, between the additive packages and the viscosity index improvers and things going on, it could be 80% base oil, 90% base oil, but you have a much more robust additive package. Now you have things like MODTC, a molybdenum additive that can be an antioxidant, an anti-wear additive, and a friction reducer. All three, a 3-in-1 that can work synergistically with the ZDP to help improve the performance of the oil. So we've got synthetic oils. We have hydrocracked mineral oils that can do a better job than the previous generation mineral oils could do in terms of handling the high temperature for the turbocharged direct injection engines. So you've got products now that can do things that products before just slap couldn't do, right? And the cost to certify, not even manufacture, not even develop, the cost to certify one of these oils is typically going to be around $500,000 to upwards of $1 million, depending upon what it is. Diesel oils usually cost at least $1 million to certify if you pass everything the first time. And almost no oil passes all the tests the first time. And then so it costs a lot of money. It's a lot of time to pass all these tests, which are very rigorous, which is why oil performance is getting better and better and better, which has allowed them to make lower and lower viscosity oils to get more fuel economy. And let's be clear, the main reason, the number one reason for lower viscosity oils is for fuel economy. It's CAFE requirements. If you think it's any other reason, you're wrong. The main driver for low viscosity oils is fuel economy. That's why there's 0W8 in my daughter's car. Is because that's what Toyota wants, because it's the CAFE requirements. That engine would run just fine on a higher viscosity oil, but it wouldn't get as good fuel economy. Therefore, they don't spec it. That's just the fact truth. It's what it is. Okay, next slide. Now, how do they know that those oils are going to work, even that lower viscosity? Engine testing. And we mentioned earlier, there's so many more engine tests now that have come in. So now we're using the 5H test, which is a deposit test. You're using the Ford 4.6 liter V8, and we're running it, and you're measuring what kind of deposits form in that engine. You're using the GM 3.6 liter V6, and we're doing fuel economy with that. And we've got, so here's a diesel engine. We're using the Volvo Mac, old Volvo Mac engine. And we're doing all these engine tests to verify the performance of the oil before it ever goes to the market. And one thing about these engine tests that you need to know is when they're testing an oil, they're not just testing the candidate oil. Every engine test runs with 3 oils. They run the failing reference, the passing reference, and the candidate. So they know that for that test and to be validated, and for that test to be valid, they have to run the failing candidate and make sure that that failing candidate fails. Put the engine back together, back on the test stand, run it again, and now it needs to hopefully pass with your candidate oil. Take it apart, redo it again, and then run the passing candidate test and make sure, okay, how does it pass? I mean, did it barely pass, or where did it go? So every time you run one oil, you're actually running 3. And for example, with the fuel economy engine test, they don't have to tear the engine apart, but they do have to do that flush procedure. And what they do there is they basically run the oil, your baseline oil, your standard. Then they dump it with a flush oil. and they run the flush oil through to clean out the reference oil. They put in the candidate that we're going to test and run it to establish the additive package, dump it, put in fresh of the candidate, and then run it both new and aged. And then when they go back, they got to run the flush oil again, put in the reference, run the reference again, flush it, put the reference in again, and run it again to make sure what's my margin of error, what's that window looking like, and then where we're in the middle compared to those. So this is the process. We're about double flushing, things like that. This is why it's so important to, if you're going to do testing yourself, you need to kind of follow the same procedures they're using to do this. That way you can get trustful information that you can rely on and not fool yourself. Because it's very easy if you just go back to back to back to back, completely fool yourself and get erroneous results, which happens really, really often out in the field. So just to give you an idea of how many engine tests there are, check out this giant list. I'm going to get my face out of the way so you can see all the engine tests that are involved with the API SP spec. You've got the 3H, the 4A, the 4B, the 5H, the 6E, 6F, sequence 8, sequence 9, sequence 10, and these two JASs. Now, all of these tests do not apply to every viscosity grade. So it's not like every oil has to pass every single one of them. Some of these are for certain viscosity grades and for other ones. But the reality is you get an idea. Look back, let's count that list again real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11. And I think it's usually about 8 or 9 tests that the oil has to pass for any one viscosity grade. That's a lot of engine testing. And you can see, I'm going to go back to it again. They're all kinds of different engines, and they're running in different configurations. Best way to say it, right? So you've got some of them that are looking for cam wear. You got some of them looking for piston deposits. Some of them are looking for rocker sludge. That each test is designed to discern a certain thing. So it's testing this one aspect of the oil, be it low speed pre-ignition performance or chain wear or deposits or valve train wear. It's looking at all of those things, and that's what the specs are. The specs are looking at all that, and that's just the engine tests. Those are all the lab tests. Those are just bench tests. Now, let's go a little bit closer to the bench test so you get a good idea what we're talking about, because none of those bench tests are bearing testers or any of the other stuff you typically see on YouTube. We're talking about measuring the viscosity grade. We're talking about measuring foam. We're talking about measuring filterability. We're talking about age pumpability. We're talking about temperature deposits in terms of like deposit control, volatility. Speaking of that, let's have a little quick discussion about volatility. So that's one of the things that's coming up, is that the traditional NOAC test, which has been a very high temperature, short duration test for how much the oil evaporates off. There's a lot of talk, and some of the Japanese specs have already addressed it, that they're going to change the NOAC test because they don't trust it, that it's not really a test that correlates well in the lab to what happens in the field. So what they're going to be doing is to still do the same test device, but lower the temperature, extend the duration, and that they're seeing stronger correlation to what really happens in real engines in the field with the modified NOAC, where they bring the temperature down and extend out the duration of the test. So that's not in SQ and GF7, but it's probably going to make it into the other ones. It was debated at the very last minute, and it's like, oh, it's too late to do it. It's too big of a change to make this late in the day. Blah blah blah. It's too soon before the launch to make that big of a change to everybody. So that just know that that is a change that's coming because, again, some of the JASO specs are already incorporating that now. They've already adopted that. So it'll make its way in because it's going to happen. And it's a good thing because the previous NOAC test, there's too much variability, and it's the new way of doing it's going to be a lot better. So let's check the next slide here. What we got? Okay. Oh, boom. Ooh, this is my favorite part. All right. I'm going to open this up a little bit, man. So all this development, we're doing all this thinking on the chemistry side. Think about the application. We're putting together our best ideas. We're going to the dyno. We're going to the lab. We're doing all this testing. This is the fun part. What did it do? And this is where you're rating and the metrology. This is, like I said, this is my favorite part. All right. The people that rate the parts, for example, you can start seeing that little picture down there. When you're looking at a weighted piston deposit, you're not just measuring the weight of piston alone. They're actually looking at the color and the morphology of the deposits. And the people that rate these things are trained, and they have to be recertified on an annual basis. And they go in and it's a rigorous process to be a parts rater. So they're looking at this stuff, and there's specs and everything to determine what is the merit of that. And so there are things like, stuck rings and piston deposits and other parts of the engine, cam wear, and they're using, only the raters, we're also using things like the profilometer, and we're measuring actual cam wear, and we're using used oil analysis as part of the API, SP, SQ specs. We're looking at what is that wear metal, how much iron is in the oil after so many hours, and what does that look like in terms of cam wear, in terms of what that shape is and what the depth of that is, what's the width of that wear scar. So you're using profilometers to measure all of these things. And that's where the key part to me is we did this work, we figured it out, did the testing. Now we know where we stand, because the API, there is a minimum to pass all of those things. Some oils are valedictorian. Some of them are A students. Some of them are B students. Some of them are C students. But you're not going to know which ones they are. If your C's get degrees, then it doesn't really matter which one you use. Just you just want to be C's get degrees. If you want to be the A student, you got to do a little bit of work. You got to do trial and error, unfortunately, to find which one actually works the best. And just looking at a virgin oil analysis and looking at the calcium levels or the molybdenum levels isn't going to tell you everything you need to know, because it's the synergies of those systems and how they work for your application what makes the biggest difference. And I wish everyone had access to this stuff all the time, because it would be so cool to actually see what did those oils do? What did they really look like in terms of intake valve deposit buildup? What do they look like in terms of stuck rings and ring groove deposits and bearing wear? This is the stuff that I wish everyone could see on every oil. But the reality is, not every oil is actually tested this way. That's one of the hidden secrets of the industry. There's called viscosity grade read across and base oil interchange. What you can do as an oil marketer is you can run your lowest viscosity. So for regular ILSAC, that would be 0.20. You do 0.20. If your 0.20 passes all the tests, you don't have to run the 520 or the 530 or the 1030. Because they're saying you ran the lowest viscosity, whatever one you ran. If you ran all the way to 0.8, if you pass it, then everything above it is good. Now, you saw that on the chart, there's only certain engine tests for certain viscosity grades. Really, when I say you really doesn't, 0.8 doesn't supersede everything. You got to kind of figure that out. But typically, if you can pass the 0.20, that means you get a pass on everything higher in viscosity than that. So you don't even have to run all of them. And then there are certain base oils that you're allowed to interchange in between without having to rerun the test, because there's just not enough testing capacity to test every single brand of oil in every single viscosity grade. Just can't. It's too much. So, and it's the additive companies, Lubrizol, Afton, Ornite, Infinium, that are doing all this testing. It's not the oil marketers typically. Very few oil marketers, Valvoline, that had their own test labs, so they can do it themselves in terms of ASTM testing. This type of testing they can do internally. Other companies don't have that ability in the US. So the marketers aren't doing this. They're relying on the additive companies to have done it, and they follow the formulary that's provided. We talked about that in the Making Motor Oil video, that how, the secret the oil companies don't want you to know. That was just it. I was talking about that. They're not doing the testing. Ad companies are doing the testing and giving them a formula. And as long as they follow the formula, they get the license. They can put the sticker on the bottle, and they're good. It doesn't mean it's subpar. It just means you don't know if it was a C student, a B student, or an A student. You just don't know. I wish this kind of data was available on every brand, right? Even if what their lowest viscosity they pass with, man, I wish this was available because it'd be so cool. But no one's ever going to show that, right? This is not going to happen. I get it, but it'd be cool if everybody could see that, though. All right. The other part of this isn't just those things. It's also the sludge and the varnish, because again, we have multiple tests. And there's a difference between sludge. Sludge typically is something developed at low temperature. So that the one test they do that, they actually cool the engine. They run it at cold temperature on purpose in order to build sludge. Varnish is developed at high temperature. So you got to run different engine tests to run varnish versus sludge because they're formed at different temperatures. So when you see something like sludge, that's low temperature operation. That's short trip driving, things like that, cold weather. When you see the varnish, that's that high temperature. So think about turbochargers and things like that. Engines that run really, really hot in the desert, you're going to typically see more varnish than you're going to see sludge. Sludge, you're going to find that in the upper Northwest and or upper Midwest, and the Northeast when it's super cold, places like that. Now, one thing that's pretty neat is a lot of the major oil companies and additive companies, especially, they own their own taxi fleets. So they'll take these products and they'll put them in their own taxi fleets, and because they have a lot of idle time, so it's really hard on the oil. Then they'll actually take those engines and those oil samples from those fleets, either partner fleets or company-owned fleets, and get that feedback and filter it in to help make better decisions about how they improve the formulas of the oil and make things work the way they need to work. All right, heavy duty diesel. We're getting near the end here. We're coming down the home stretch. So in the diesel oil range, just like we kind of saw with the gasoline, that you've got your 020s and up, they kind of treat them different than the 016s and down. You see the same thing now with the diesel. So the API CK4, that's like your 10W30s and higher. Then there's actually a FA version of 10W30 that's actually thinner. So the FA4 is a different spec than the CK4. FA4 is not backwards compatible. Just like the 016s and the 12s and the 8s are not backwards compatible, the FA4 oils are not backwards compatible. The FA4 is fuel economy, right? It's fuel efficiency. That's what it's all about. So they typically have a lower high temperature, high shear. So they're actually thinner in the engine in actual operating environment to squeeze a little more fuel economy out, because diesels, they're feeling the same pinch in terms of fuel economy and emissions that the gasoline engines have been under for a long time. So here's a kind of an overview really quickly of the tests. You can see there's just as many tests for a diesel engine oil as there is gasoline engine oils, and the different ones. So like deposits. So the C13 and the Cat 1N, those are tests strictly for deposits. The MAC T11, that is soot handling. I mentioned that earlier, that, soot is a big issue, and that all of these tests are designed to address certain operating issues, and soot's a big one. And that MAC T11 has been the workhorse test for decades in terms of soot handling, to make sure that, does this oil do a decent job? Does it pass the test in terms of being able to protect the engine from soot related wear? So that test is all about. Then of course, we got some wear tests, the Cummins ISB, the MAC T12, you got the roller follower test. All these tests are related to wear. Then of course, you have some aeration test as well, which is the CAT C13 aeration. Because again, a lot of these engines, you get build a lot of oil in them, but as the engine runs, especially at low temperature, viscosity is higher. It's very easy to get a lot of air entrainment in the oil, and that negatively affects the lubrication properties of the oil, especially when you have things like the HUE injectors where you're using oil as a hydraulic fluid. All these things have to do a good job. That oil has all those different jobs that it has to do. It's really tough. Now, speaking of injectors, we just did this video, came out last night, actually, a collaboration with the Repair Geek, where we actually look at diesel fuel additives. I highly recommend going and checking out that video if you have a diesel engine, because there are some true advantages to running the right diesel fuel additive, because it can actually help extend the life of your engine as well. So to sum everything up, and then I'll try to answer some questions for a little bit until we run out of time. I got to go by the top of the hour for certain, but I'll do what I can to answer some questions toward the end. Is proper lubrication is always the 4 R's. Right oil, which means it's the right viscosity and additive package for the application. And it's at the right place, at the right time, and in the right amount. That is the key. A lot of times you look at lubrication related problems, it's not always the lubricant's fault. Sometimes there just wasn't enough oil there, or it didn't get there when it was supposed to be, or enough of it. So when you have a problem and you think it's lube related, ask yourself these 4 questions. If I've got the right viscosity in the spec additive package for what I'm doing, that's probably not my problem. Is there something else? Now, the caveat to this is it has to be clean. Filtration is a huge, huge issue. Doing the used oil analysis, speed diagnostics, it's pretty common to see higher rates of wear in an engine when there's a higher level of silicon, dust, dirt entrainment getting in to the engine, because they either haven't maintained their filter or air filter, or they have a really high flow air filter that's putting in a lot of air, but it's also letting in a lot of dust. Or we have a high fuel dilution. Either the injectors are dirty, or the tune's weird, or whatever the reason for the situation. A high level of contamination from the fuel or from the environment will typically cause more wear. And those are the things we see as a bigger determining factor in terms of performance, wear protection of the engine, than it does brand. I hate to say it. I mean, if you're talking about tracking your race car, different conversation, right? But for daily drivers, contamination's your biggest enemy. When it comes to track cars, chemistry usually plays a bigger difference there. So not every application is the same, so they don't all have the same needs. So with that, while I have a little bit of time, I'll try to answer some of these questions. I know there's like a giant million of these things. Let's see here. Y'all are talking to each other in there, so that's pretty great. Yeah, don't put seafoam in your crankcase. I mean, it will evaporate out right away. I mean, there's no reason to put anything in your oil, in your motor oil. Like, there's just not a reason to put stuff in your motor oil. As we just covered all of this, that there's a massive amount of engineering and testing that goes in to developing that engine oil. When you go put something else on top of there, you're just playing chemical Russian roulette. Might work good for you, might work bad for you. You just don't know. And my dad taught me risk versus reward. And I know the chances of that additive really making a giant difference for the positive, probably not going to happen. So I'd rather avoid the risks. Yeah, I've seen the one advantage I have, that's the unfair advantage, is that I see hundreds of used oil samples every week from all kinds of different applications, from all kinds of viscosities. Just so when I have an opinion, or I say opinion, when I say something in one of the videos, while I may not have all of the test data right there that confirms everything I said, it's not really my opinion. It's what I've seen from the data. I just don't bring all of the customer data and put it into all the videos. I've just chosen not to do that. Now, maybe I should. Maybe I should find a way of removing customer information and dealing in aggregates and showing things and proving it out through the co-op. Really, it's you guys, the viewers, that help support me by choosing to do your oil analysis through Speed Diagnostics. We have this amazing collective information where we can say very definitively about certain things, like do this, don't do that, because we have thousands of data points that backs it up, that comes to that conclusion, right? We're not saying this is my theory, let me go cherry pick the information that I want that validates my opinion. It's the other direction. It's like, wow, all the data says this is the fact. Well, okay, well, data keeps saying it, then that's what it is. And you can't run 2,000 engine tests in a single YouTube video to prove something out, because you can't, cost-wise, you can't do it. I'm not Mr. Beast, right? I don't have unlimited budgets to make shows on Amazon. Wish I did. That could be a lot of fun. Go buy Southwest Research and just do all this stuff and make videos about it. I don't think the economics of that are going to work. So we try to do a lot of times with the video is take a concept, but we already know what the reality is based on all the data we have, and then create a scenario that replicates and kind of shows that this is what happens. And it is only one. It's not a standalone. There's not a control and all the other stuff, to do the lab method. But the conclusion of the video isn't derived from the test in the video. The conclusion of the video was derived from the thousands of samples that we already have, that already say, well, this is what really happens in the real world. So the test sometimes just mirrors what reality is, and we go from there. I hope that makes sense to everybody. Didn't mean to get off on a rant like that. What else we got here? Oh yeah. Is Pennzoil Platinum or Valvoline EP? I'm not sure what the EP is. Maybe major RP. Good for a tractor and generator. Yeah, I'd say so. I mean, the Pennzoil Ultra Platinum has a very robust additive package in it. So being that it's full synthetic, in terms of it's a GTL based with a good additive package there, API, SP, got a great antioxidant package there. Yeah, that's one of those things where the modern stuff now, because of the demands from turbocharging direct injection, where that statement wouldn't have been true 15 years ago, it is true now. So I would definitely look at doing that, because that would be totally fine to do that without any issues. Let's see what else we got here. Blah, blah, blah. I mean, wow. I mean, you guys, what makes DEXA so special? So I have a love-hate relationship with Dexos. So actually was good friends with a guy from GM that ran the Dexos program. He actually lived here in the Charlotte area for a while, and we had lunch several times together and discussed a lot of things. GM got tired of the slow movement of that giant committee, right? We go back, what slide was it? Where we showed all the different people that are involved in, all those different organizations, right? Look at that giant list. You know, it's hard to get all those people to agree on anything. So GM was getting tired of the fact that you had very diverse manufacturers. You had people who had really small engines, you had people with really big engines, you had people that were big into turbocharging, people who wanted to stay NA. You had this diversity of opinions in what direction they should go, what needs matter to them. And GM said, we're going to go do our own thing. We know that we need new engines for where we're going. So we're just going to go build our own specs, our own engine tests around what we're doing. We'll still play over here because we understand that there's a need to do that. We're not going to leave you guys and just leave, but we're going to run our own system parallel that focuses on what we need for us. That part's awesome. And they went and developed, rigorous standards to meet their needs so that when you see a Dexos oil, then it will be a C's get degrees for your GM vehicle. The downside is the Dexos licensing scheme is really expensive because now you only have the volume of GM cars and trucks to support all that testing. And that testing is really expensive. So GM wasn't going to underwrite that this whole program's got to pay for itself. Maintenance, development, R&D for the future. So when you buy a Dexos licensed oil, the licensing fee that goes to GM is a lot higher than an API. API is like tenths of a cent on the gallon or quart, where you're talking about, nickels and dimes per quart for Dexos. It's big difference. I think it's like 75 cents a gallon, I think, or at least it was at one point. With Dexos, where it was like 5 cents a gallon for API. So big differences in terms of licensing scheme. The other downside too with Dexos, or I say is ups down, right? So we mentioned earlier about there's base oil read across. And you could have, one oil passes one viscosity grade, and then you can read across. And then you could also say, well, all these other base oils all fit within that same family of base oil. So they're interchangeable. So I only need to run one test. But Dexos, it doesn't work that way. For each base oil formulation you use, for each viscosity grade that you want to license, you have to pass that one. So there's no more read across. So for example, you can go look at the Dexos license, right? Go look at the website that they show all licensed brands. You're going to notice that for, say, the AC Delco, their own house brand, 0W20 synthetic, the same spec, there's like 4 or 5 different license numbers. That's because they have 4 or 5 different base oil formulas. Because the full formula has to be licensed. So when you have an ultra platinum or a restore and protect or some kind of unique special oil, they have to know every component in it. They license the entire formulation, not the DI package. And that's the difference. So hope that helps explain a little bit about why all that stuff changes around so much. Let's see what else we got here. Anything else? I mean, anything else? I say that like there's not questions. I don't even know. Like on the StreamYard side, it doesn't tell you, oh, here we go, do this. All right, here, let's go do this. There's a, no, thank you everybody that said, super chatted and all that. Great appreciation. Let me see where this is. Okay, point of view on transmission fluid, the ultra low viscosity transmission fluid for say Valvoline versus Mercron. Okay. The same thing that I said about engine oils in terms of there's only 4 additive companies. That same thing applies to transmission fluids. That those same four companies, Lubrizol, Afton, Ornite, and Infinium, are the only companies that make gear oil and transmission fluid packages. And really, the two key ones in that, the two big players, are Afton and Lubrizol. So almost every brand of ATF or gear oil, they're added to packages coming from there. But as we noted, base oils can change. And so now the good thing about, let's say, Valvoline in this case, because we have a very specific one, Valvoline versus Mercron. So Valvoline has their own test lab. So they could do something a little bit different if they wanted to and be able to have an advantage. So they're unique because they have their own test labs and they do a lot of work with OEMs. So people don't do oil sampling as much on transmissions and stuff as they do other things because the fluids can last for a lot longer because they're not being contaminated because there's no combustion going on. So back to this. C's get degrees, use the spec that's called for, and you're good. If you want to be valedictorian, you're going to need to do oil analysis to find out, does the generic brand versus the name brand make a difference? There's a good possibility they're the same, but you don't know that until you test it. And that's a just trial and error process, unfortunately. If a crank is scored a bit and you just put in new bearings, and then oh man, if the crank is scored, that surface roughness on the crank will probably end up wiping out the bearing. While the engine's running, you should be full film. But if there's anything that's pushed up, it could rupture the oil film. That's why when you wipe out a bearing, you always have to have the crank polished, because that crank journal is the one that needs to be perfect. The bearing could actually absorb other things and be misshapen. And I say misshapen, but it can have some imperfections in it and be okay in terms of it can. That's why there's a lead overlay. Is it softer so it can embed debris and things like that? The crank's hard. So if you've got a hard, rough surface, what's it going to do? It's going to kill that bearing. And so that's no good on that. Make sure I got everyone's super chatty questions in there. Okay. Okay. He's not able to find the Pennzoil Ultra Platinum in 10W30 for a small engine or the Valvoline Extended Performance in 10W30. If you can't find one of those in 10W30, well, I would think, I don't know. I don't think the mobile truck and SUV formula is available in 10W30, but you might see that if Valvoline has the advanced 10W30, because the Valvoline advanced full synthetic is pretty good. If they had the advanced 10W30 in there, that one would do a good job as well. So unfortunately, that most of these, like the really good stuff, is focused on the lower viscosity grades because that's that ILSAC area where the majority of the market is. So when you get into the 10W30s and stuff, it's not as there. Your other option is look at a specialty oil, right? There are, the hot rod type oils and stuff like that, the high performance oils. A lot of those are very robust formulas as well. Now they may be just as expensive as your, small engine oils are. So there's not a cost advantage to doing that. But, if you really want to know the most on that, you might want to do oil analysis, right? Do some samples of your OEM oil that you've been using and see what it does and try others. I mean, heck, the VR1 might be a good option that you can find. It might be more affordable and could possibly do a better job because the VR1, even though it's got boosted anti-wear stuff and it's for racing, it's based off of a standard API SP package. It's just boosted up. So that one could be something to look at as well. Let's think of anything else. What else we got in here? Okay, question about Valvoline restoring protective seals. That's a question I see all the time. So there's nothing in, to my knowledge, right? Because I don't know all the formulation details. So obviously, I don't work for Valvoline. I know Roger, and I know Michael, and I know some people at Valvoline, and they're good friends, and they've been able to work on some projects together, which is great to be able to do that. But I don't know the details of Restore and Protect. In fact, I wouldn't want to know that information anyway, because then I would want to tell everybody, and they don't need to tell me because I don't want to tell everybody. I don't want to be that guy. I want to keep secrets. So I do know this from looking at the FTIR results and just the chemical analysis of it. There aren't esters, there aren't strong esters and a high level of esters in that formulation. And it's those esters are the ones that can degrade the seals. So there's nothing in the Restore and Protect that's going to be aggressive toward the seals. It's unlike some of the other products that are out there that can do some cleaning stuff too, where they tend to be more aggressive using esters to do that cleaning. That same esters are aggressive as seals. That's not the case here with Restore and Protect. But yeah, right. Yeah. Race car engines are not made for high mileage. They're made for high temperatures. So you're talking about lawnmower equipment, yard equipment that's air cooled, those high temperatures. Sometimes the race type chemistry, not racing only. Racing only is bad. Racing only means it's usually low detergent. And that would be a problem in that application. But, Pennzoil Ultra, I mean, really, for 0W8, you're talking about a Toyota. And the Toyota 0W8 is actually really good. I haven't tested anything else other than that, but I would stay with that because I know that the 0W8 from Toyota has a pretty good additive package in it and seems to be fairly decent. So I would assume other 0W8s are going to come to the market. I know Mobile One has a 0W8 that I've been told is available. I haven't seen it in the real world yet, but I hear it's out there. I would not assume that the Mobile One 08 is the exact same as the Toyota 0W8. That does sound like something I need to investigate and to look into. Yeah, you can use Restore and Protect in a brand new vehicle and run it forever. There's no issue with that. Concerns of missing. Yeah, I don't like mixing esters. That can be a big problem because some of them don't like each other. Again, ask me how I know. I have seen that picture show, and it is not a lot of fun. See what we got in here. Okay. All right. So, question about the non-Euro oil in a Euro car. The big issue with this is most Euro oil specs has to be mixed fleet, both gas and diesel. So we talked about earlier the dispersant package, how the dispersant package is very different in a diesel versus a gasoline engine. So for a gasoline engine, you can run a API oil in a gasoline engine. Now, I would say you need to be doing used oil analysis to make sure that there's not something weird, right? Because sometimes they'll have some really funky high temperature, high shear specifications, and they're there for a reason. They found that the hard way through doing their testing. You need this. Now, the question is, was that needed for the gasoline engine as well as the diesel engine? It may have been just for the diesel side of the house, not the gasoline side of the house. If you do the used oil analysis, then you can know for a fact. But I wouldn't go off script away from the OEM specification without used oil analysis. If the used oil analysis says you can do it, everything's good, go right ahead. If it says you need to go back, then go back. Just follow the data. Don't speculate. Trust the science. The used oil analysis can give you the science and get you there and keep you safe. Amsoil versus Torco. I'm not testing that one right now. Oh my goodness, man, you guys are killing me this morning. This is fantastic. Killing me, and I'm saying that in a good way. I love everyone showing up and all the questions. This is pretty amazing to have this kind of turnout and everyone on board. This is cool. I'm glad you guys love this stuff as much as I do, because I do really love the science of motor oil. It's like most things in life, it's good to have passion for something and be excited. You don't want to go too far and become extreme, you know, but it's good to care, right? I'm always that kind of person. We want to win races. We want to win championships. We want to do the best. I want to be valedictorian when it comes to this stuff. So we're going to push hard and focus on little details, because that's where the big advantages can come once you get past the basics, but it's these kind of things that we talked about in the presentation. These are the basics. When you know these things, then you can move on to the next level, and you've got a firm basis of knowledge, which means you can continue to climb the ladder without having to worry about slipping back because you didn't miss anything. All right. So we'll continue to do some more of these live streams in the future. And when we do, we're just going to keep leveling up. We're going to go from strength to strength and kind of building up, so that as a community, we're all learning together and we're getting better as we move forward. That way we can make sure that we're all collaborating, right? And that's the things that you guys, and like you did here in the chat, help each other, right? That, I'm not the Oracle of Delphi. I don't have the knowledge and just the infinite wisdom to be able to tell everyone, oh, do this in this engine. That's going to work perfect. I mean, I wish I did. I help everybody I could, but I don't. Other people are going to have different experiences and skill sets and application details that can help somebody else. So creating a community here where everyone's able to help each other and share their results and experiences is really helpful. So hopefully that's can be our mission as we'll call it the Motor Oil Geek community for 2025, is that, it's just not one way, it's multi ways that we're all helping each other. And I'm going to do my very best. I commit to you guys and gals, 'cause I know it's not just guys watching, guys and gals, that we're going to keep showing up, making videos that bring value every single month. I'm going to try to do at least 2 videos every month. I was able to do that last year. That's my commitment to maintain, try to do at least 2 videos a month this coming year. And each of those videos is going to provide some nuggets of wisdom and value that hopefully you can actualize to make sure that you're getting the most performance and durability and value out of your vehicle and your choice of oil and how you choose to maintain things. I've got some pretty cool partnerships lined up. We mentioned filtration on the side earlier. We're going to have some fun field trips this year. Let's say it that way. And so hopefully all of this makes a lot of sense. And oh man, that's crazy, man. You guys have been over the top. I can't thank you enough for coming and hanging out on a Saturday. Like I said, 2025, there's going to be some really fun field trips. There's some great stuff coming. Thank you so much for supporting me and the channel and building what this great community can be to, as one of my buddies called it, said, you're making motor oil great again. I don't know. That sounds too political to me, but hey, here's the thing. We're here because we care. And thank you so much for showing up, showing your care, helping support us. Thank you so much. Have a wonderful new year, and I'll see you on the next one.